Now we're going to talk about limits of sequences. So just as an example, let's consider that the sequence rule is 1 over 2 to the nth power. So 1 over 2 to the first would be 1/2, 1 over 2 squared, 1 over 2 cubed, 1 over 2 to the fourth, 1 over 2 to the fifth, and so on. So we look at as the exponent increases, the terms in the sequence are getting closer and closer to zero. So as the exponent gets bigger, we see the numbers are smaller because the bigger the denominator, the smaller the number. So what we say is if we were to keep the sequence going, we are getting closer and closer to zero every time we go a step further. So we are going down towards zero, so the sequence is said to converge. It doesn't have to go to zero to converge, it just has to come down to one number, where the further you go in the sequence, the closer it gets to a certain number. In this case, it's getting closer to zero, so we say the sequence converges to zero. Limits are used to define convergence, and so that's saying that if we take the limit and take the number of terms to infinity and we get a number, then it's said to converge there. So a sequence is said to diverge if it's not going down to one number. For example, this sequence where every time you get closer or every time you go further in your sequence, it changes values. So it goes from -1 back to 1, -1 back to 1. So this is said to diverge. Or if the sequence was getting larger and larger every time and going to infinity, then it's not going to one specific number. So it would be said to diverge. The following three rules for sequences, we're going to look at the limit of the sequences and see if they're converging or diverging. So let's start by looking at the sequences themselves. And we're going to plug in some numbers and see what the sequence does. So if I plug in 1 for part A, we would get 3/5. If I plug in 2, it'd be 5 over 6. 3 would be 7 over 7. 4 would be 9 over 8. 5 is going to give you 11 over 9. And 6 will give you 13 over 10. And we can continue this on and on. What we see is that the top is going up by 2 at a steady rate. So it's going up by 2. And the bottom is going up by 1 at a steady rate. And so the further we go, we're going to see that these numbers are going to get closer and closer to the number 2. So we say that this sequence converges to 2. Let's do the same thing with B. So if I plug in 1, I get 3/5. 2 gives me 5/8. 3 gives me 7/13. 4 is 9/20. 5 is 11 over 29. And 6 is 13 over 40. And so we look at this sequence and we see the top is going up by 2 every time. And it looks like the bottom goes up by 3, and then 5, and then 7, and then 9. So the bottom is getting larger faster than the top is. So it's not steady like it was in the first one. And if the bottom is going to get bigger than the top and at a faster rate, it's going to get a lot larger. So we say it converges to 0. This converges to 0 because the bottom will eventually outweigh the top and give you really small numbers. And then C, if you plug in 1, you get 3/4, and 2 is 9/16, and then 19/36, and 33 over 64, and 51 over 100, and we could keep going. And so what we see here is the top is increasing, and so is the bottom. And the further we go, we can kind of start seeing it here. We've got almost 20 over 40, and then here 30 over 60, and then 50 over 100. And so we can see that the further we go, the closer we're getting to 1/2. So this converges to 1/2. Now, that's not always an easy way to decide whether it's converging or not. So what we can look at is our exponents like we did in the last page, where you consider the degree of the top and the bottom. And so here we see the degree on the top is 1. This has an exponent of 1, and the bottom degree is 1. And so since m equals n, since the degrees match, then we can say it's the number in front. So it's a over b, which in this case is 2. So that is how we could get the answer of 2. Here we see that the top degree is 1 and the bottom degree is 2. And so here the top, which we call n, is less than the bottom, which we call m. And so if we look at our table, we see that that would be 0. So it converges to 0. And then C, they've got degree 2 and degree 2. And so again, they're equal. The top equals the bottom. And so it would be the number in front, or 2 over 4, which is 1/2. So that is why it is converging to 1/2. On example 5, they're asking us to find the limit of the sequence with this rule. And so the limit of the sequence is how far can we take it. So what we're going to do is go ahead and introduce this idea of a limit where we're taking the number of terms to infinity. And so what we're going to do is simplify this as much as we can so that we can evaluate the limit. So what we're going to do is first start with foiling. So I'm going to have an 8 and an n. And then if I FOIL those two parentheses, I'm going to have 2n squared plus 1n plus 2n plus 1. And on the bottom, I've got a 6n cubed. Here I can cancel one of my n's and go ahead and collect like terms. So I've got then an 8, and I've got 2n squared plus 3n plus 1 over 6n squared. If I distribute my 8, that's going to give me 16n squared plus 24n plus 8. And then if I want to evaluate the limit, this is kind of what we did earlier. We're going to divide by our largest exponent on top and on bottom. So then that would give me 16n squared over n squared, 24n over n squared, 8 over n squared, and 6n squared over n squared. And then we simplify it. So that would be 16 and 24 over n and 8 over n squared, and then 6. And then if I go ahead and plug in infinity, I get 16 plus 24 over infinity plus 8 over infinity squared over 6. And anything with infinity on the bottom becomes 0. So we end up just getting 16 over 6, which reduces down to 8/3. And so that is the limit of the sequence. And so we would say it converges. If I were to get infinity or negative infinity, I would say that the sequence diverges.